Welcome to Space Terminal, the show where we sit down with leaders defining the next century of space infrastructure. Today, I'm joined by Julie Newman, VP Engineering at Outpost Space. They build cargo ships in orbit. Our listeners are founders, operators, officers, and partners building frontier technologies. Welcome, Julie.
Hi, thanks so much for having me.
Thank you for joining us today. You get the call to join Outpost Space in 2024. Why you?
My background, I've spent my entire career in space. I started studying electrical engineering at Caltech and then used that to have a stint at SpaceX, then spent 7 years at JPL working on some really cool satellite missions, some Earth satellites that are flying today, also a mission to Jupiter, where I was a lead on one of the instruments. Then also spent a good chunk of time at Boeing, working on their satellite division, also worked on their rockets, their crew capsule, and was chief engineer for a geosatellite program when I got the call for Outpost. And it was really an exciting time. Over my career so far, I have sent satellites to every different orbit and to interplanetary space. And I really saw Outpost as that final connection back to Earth of now going from LEO orbit down to the ground with this reentry vehicle.
You have imbibed avionics across your career in SpaceX, at NASA JPL, and Boeing. What made space logistics the next frontier for you?
One of my favorite books actually is a book called The Box, which is all about the shipping container and how, despite its humble appearance as an invention, it's actually probably one of the most impactful inventions of the 21st century. In the span of about 7 years, the invention of the shipping container really revolutionized the entire global economy. And what we're doing here at Outpost is very similar. So up to this point, the space industry has primarily been all about data and bits and just about the communication to space and back or through space. But what we're doing here at Outpost is we're now connecting space to Earth with real matter and not just with RF signals or optical signals. And that really is going to be such a game changer that so many people don't realize yet.
I'm going to ask you to rank these variables from 1 to 4. 4 means it's mission critical in 2026. Radiation hardening,
3.
thermal management,
Oh, that's a 4.
spacecraft maneuverability,
That's a 4.
space debris mitigation.
That's a 5.
Okay. Component modularity.
I'll put it at 2.
Okay. Can you dig into space debris mitigation management? Why is it a 5?
With the expansion of the space industry, obviously that means there's a lot more things in space. And to the other item of maneuverability, that makes maneuverability that much more complicated and important as well. With all the new things that we're sending into space, it's really important that newer companies coming in or new endeavors in orbit are being good stewards of space. And the biggest thing for that is mitigation of debris and preventing our orbits from looking like these trash piles of leftover things. I'd say as an engineer, I'm often thinking about risk, right? And technical risk and schedule risk and things. And truthfully, one of the biggest risks, if I were to put it on the humanity and certainly the space industry leaderboard, is the Kessler Syndrome of if there's too much debris in orbit, it really hampers our ability to do much of anything with space. And our current economy is already so intertwined with space operations that in the future economy, it will even be that much more important. And so for any space company doing operations in space, it's really important not to be leaving debris and to be making sure that things are not waiting around up in space or becoming inoperable in space so that they're not a hazard for other things in space. And for Outpost, our reentry vehicle, we're actually one of the only currently or stipulated reentry vehicles flying that brings 100% back of our vehicle. We don't leave any portion in space. There's no tug, there's no satellite bus that gets left in space. We are bringing it all back every time we re-enter, and then we can reuse that satellite bus and that full system again for the subsequent launches and reentries.
Why is reusability so important?
I think we all have the understanding reusability is important just for, again, that stewardship and that value. But the other big piece is economics. when something's reusable, this is the example obviously of the SpaceX model, once you have a system that is reusable, you're just in a complete step above any other system that's not reusable. We see that as really important, especially as one of our primary goals at Outpost is to really open that return lane from space and make down mass as economical as up mass, which would enable a lot of really cool industries and applications, in particular in space manufacturing applications, as long as it's economical enough to make these really cool technologies in space, then we will build out that ecosystem. But until we hit that threshold, that activation energy level of making it possible to do business in space and in reentry, then you can't. And so reusability is a big part to that.
90 minutes to deliver cargo on a pad anywhere on Earth. How?
You think of the Earth as being very big, but when you go at the speeds of orbit, it's very fast. So many of the listeners on the podcast will be familiar with spotting the International Space Station in the sky. And if you've ever done it before, you'll know that it tracks across the sky relatively quickly for the field of view that you're able to see. And that's the speed that our spacecraft are going approximately while they're in orbit or if they're doing a suborbital trajectory. The fact of the matter is, from launch, you could get into orbit and then re-enter from there and do our full landing sequence, which is our reentry burn, our heat shield deceleration, and then our controlled autonomous paraglider flight. And that full sequence is in about 90 minutes or less, depending on how close or how far, but you can get to the other side of the world in 90 minutes. Yep.
And let's zoom in on what you're actually carrying, the shipments, the cargo. What is the container capacity? What even constitutes as cargo? And who outside defense is paying for this?
Our first vehicle will have is sized based off of an International Space Station standard. So on the International Space Station's equipment experiments will go up in a size called a mid-deck locker. And it's, I don't know, think like big, maybe a few shoe boxes. And we're building what is a double mid-deck locker, so it's two of those. It's about the size of a mini fridge, just to give everyone a general sense. And it will be able to carry 100 kilograms of payload. Our next-gen vehicle will then expand that. We've chosen our technology for our vehicle because it can be scaled up, and we can scale it up all the way to a shipping container size. So this is a TEU, a 10-foot shipping container that the military customers are very familiar with, that is very similar to the ones you see on, all the Amazon Prime trucks and the FedExes of the box cars. And then as far as what goes in it, certainly for high value materials is what it would boil down to. On the military side, the military cares a lot about speed, and for the right thing in the right place at the right time, that's a very valuable use case for them, and is actually a reason we have a strategically aligned product of AirDrop, which is basically taking the later portion of our flight and deploying from an aircraft instead of deploying from space, which gets them what they want even sooner than these orbital missions. What you would put in there could be any sort of life-saving equipment that someone in the field might need. That could be, think of a downed fighter pilot somewhere that's maybe bobbing in the ocean or stuck on a little island and they can't be rescued for a while. Getting them life-saving materials, getting them a raft, that's a very valuable use case. Then actually one they keep coming back to and discussing with us is actually fast transit of blood plasma. So if you have wounded, actually getting donor blood or donor blood plasma across the world in 90 minutes. 90 minutes is, for all of those with a medical background, a very valuable life-saving time frame where if you can administer care within that time span, you can actually save the person. On the commercial side, our biggest excitement area is the in-space manufacturing. So there's a lot of materials and products that you can make in zero gravity to better quality or to something that you can't even make on the ground because you're in that zero gravity environment and because you are in what is a ultimately very stable temperature and vibration environment. So for especially crystal-based technologies, that becomes a very critical thing. You can think of it, to oversimplify, you can grow perfect crystals while in space. And that extends to a lot of very valuable optics technologies. In particular, we think a lot about fiber optics. So us internally for Outpost, we're playing the long game too of establishing and thinking early about what it would mean to develop fiber optics in space. And we've been bringing on some real experts in that field to ensure that our vehicle would be capable, and then making it capable of also building fiber optics in space.
What constraints in docking and cargo handling prevent you from scaling to USPS levels of throughput?
Nothing, truthfully. At the end of the day, it's really just launch cost and launch cadence. But SpaceX has been really doing a great job, and certainly, as everyone talks about in the industry nowadays, once Starship comes online and comes down to prices that people are stipulating, even the reasonable ones, not the crazy cheap ones. Even we don't need it all the way there. We can scale, to the level of a FedEx. And actually, when you look at the economics of that, it's suspiciously close to the premium that people will pay from, say, ground travel to air travel, right? To get it quickly is obviously worth more. And you could basically make that step again and do it through space in 90 minutes or less, and actually reach economics that are equivalent in a way. So it's actually quite crazy. We could very realistically see in, the next few decades that, like we were talking about earlier with the box and the shipping container, a through space shipping container can really change the game of the entire global logistics market.
How do you become profitable in this business?
At our unit economics, each individual launch would end up being profitable. Actually, for example, for the fiber use cases, manufacturing of in-space fiber optics, those are very profitable, I'll say, in the economics perspective. It feels very different when you're scaling up to these sizes. Typical other reentry platforms and pricing right now, it's really not, they're so small. It's actually what you can get right now is, as someone who will not be named, one of our customers was describing, the payload volume is the size of 2 ham sandwiches. And when we're taking what they're used to doing with 2 ham sandwiches and then expanding it to a full shipping container, that's just a complete game changer. And from a profitability perspective, that's not having to, you can think of it, if you only have 2 ham sandwiches, you have to distribute all of your launch cost into the value of that ham sandwich. But if now we're doing launch cost and it's this much bigger system, the economics of the impact of the launch play less of a role in the economics of the materials that are made with it.
Let's compare ablative thermal protection versus your proprietary pneumatic technology. How much are you saving in costs?
Our solution to the thermal protection system is a fabric-based system. So it is a deployable. It folds up much like an umbrella when it's on the launch vehicle, and then when we're in space, it deploys into, think of an open umbrella, and that is the thing that decelerates us when we're coming into the atmosphere. Because we have gone for this deployable, it means that we have a much bigger cross-sectional area than traditional ablative solutions. So think of like a space capsule, so like a Dragon capsule or something. Those are ablative tile-based reentry systems. For us, the difference with this giant cross-sectional area is that we actually decelerate much higher in the atmosphere and much, faster or slower, depending on how you want to describe it. But it's thermally much more favorable in the manner that we are re-entering. And that allows us as well, because of our greater cross-sectional area, we re-radiate a lot of our heat back out to the environment as it's coming in. So it's a bit counterintuitive when you get into the numbers. Our system is not nearly as hot as people intuitively expect it to be.
What telemetry or thermal protection lessons from the earlier 2 missions are you applying to your upcoming 2026 manifest?
We've built a very strong team of technical experts here at Outpost, people who have worked other reentry vehicles, people who have worked in a lot of relevant aerospace applications. And the lessons learned applying in there, we are working very closely with a team out of NASA Ames that has done a lot of research in this realm and that actually demonstrated a system like this back in 2018 at a subscale. And we're working directly closely with them. They're on our contract for our first 4 missions, and they have been a really great partnership, really making sure that nothing's getting missed and validating all of our analysis against all of their internal analysis and their decades of experience in dreaming up a system like this.
Let me summarize. You launch into space, you deploy in LEO, you secure the cargo, and then deorbit in a 2-stage descent. That sounds risky. Why is it worth the risk over a simpler capsule-style landing?
Well, I'll say first off, I love hard problems. That's why I do what I do. I think that's why a lot of people in the aerospace industry do what they do. Is it should sound crazy, and that's how we attract the best talent. Is because it is a hard problem, but doing it is so incredibly cool and also so incredibly valuable to humanity and economically to the industry. So our system in these stages. So we, like you said, we launch on a traditional space launch vehicle, notionally a SpaceX, but we are launch vehicle agnostic. We can fly on other vehicles as well. While we're in space, we act as a satellite briefly. We deploy our heat shield, and then we can either loiter in space for as long as desired. We have an interesting paradigm called Space Garage that one of our customers is interested in, of basically pre-staging those valuable cargo drops in orbit, so that, say, if a conflict arose and they needed to get something to a downed aircraft or something like that, that they would have that capability and the commanders would have that at the ready. But while we're in space, we deploy our heat shield, and then once we're ready to go, we have first a propulsive burn that begins the landing. Then there's the heat shield deceleration point. Then we have a drogue parachute, which is technically another stage from what you described. That gets us through the supersonic regime down to subsonic. Once we're subsonic, we deploy our paraglider, which is the second piece to our secret sauce of our return vehicle. So a paraglider, think of it much like a large parachute, except it's steerable. And in addition, it gives you a very favorable glide ratio. So our canopies are up at about an 8-to-1 glide ratio. So that means for think of it, every mile or kilometer down, you can go 8 kilometers or miles as 1 unit to 8 units forward. What that does for us is it means that we can reenter from space, and reentries they're very chaotic, as you can imagine, and small perturbations can mean you end up in a significantly different location downrange or to the side than what you initially expected based on your input conditions. And what our paraglider does with this range is it allows us to make up for that error during our flight under canopy. So we can then steer back to the intended landing site. So it's almost like as we're coming in, you get a wider error bar the lower you'd get, and then we bring that funnel back down to the original position because we have our canopy. This is very different from traditional capsule reentries. Capsules, it's more of, for us, we are selecting a landing site and we're thinking like a helipad size of landing. We are, with our government customers, we're promising 25-meter circular error probability, so landing in a 25-meter radius. What they're used to with a capsule-based reentry is more of, we're going to box off these few square miles of ocean, or we're going to box off this giant swath of the desert and land there. And then it makes that recovery aspect to it totally different and slower, and for certain payloads that's not viable. I'm sure you can imagine for things like some of the in-space manufactured applications, or like in-space developed pharmaceuticals or biopharma experiments. They don't usually like going and bobbing in the ocean for a few hours until they're found. They would much prefer to get their payloads immediately so they can get the data that they care about. And so for us, that precision is really game-changing. And we see that as, like to your earlier question when we were talking about space debris, to be good stewards of the planet, landing with precision allows us to do more reentries without interrupting other regular operations. We're not having to close down as much airspace. We're not polluting with ones that get lost. We're able to just have a really quick cadence. One of our marketing videos from a while back that I've always really loved shows us landing at what looks like a spaceport America. And you can really envision that as we're doing this high cadence of especially the in-space manufactured payloads, just having a regular landing, every day or every few days coming into that facility. And if it's just landing on a pad, or even it doesn't need to be a prepared landing site, but you could make it one for just faster unload. And that really just is a completely different paradigm from the capsules.
Precision landing of 25 meters within the landing zone. What's the most important variable to nail that landing?
We are executing a lot of autonomous control, and guidance navigation control algorithms are really the key piece to that. So you can think of it much like a person. The vehicle ends up flying a lot like a robotic person paraglider. It's effectively actuating like it has 2 arms that are pulling on the strings, just like you would see a paraglider flying. Teaching a robot how to fly is certainly a hard challenge. It's training the system and having a lot of flight hours to have it, have that touch much like a person would. We're actually very fortunate. It's very unique as a space company to be able to do a lot of early flight testing. But because of our paraglider system, actually a good amount of our test, we can really de-risk by doing aircraft deployments. We've got a regular facility that we use out in Mojave, out in California, where we do drop tests regularly, and we'll just be cycling back and forth. We've got a whole bunch of test units. We go out there and we're testing out the algorithm and making sure that once it re-enters, that paraglider opens like we're getting to the target, period, full stop.
In Mojave, I know you're testing atmospheric reentry with helicopter drops. What's the delta between that and actual space reentry?
The difference is primarily the altitude. So when you go to higher altitude, you have less air pressure. The air is literally thinner when you're up high. But actually, we use the helicopters more for the navigation development, the algorithm development. But separately, we have also done high altitude balloon drop testing as well, so that we've proven this system deploys and maintains its controllability at the higher altitudes and the lower air pressures. So our system, Sally, actually this one on the ground right behind me in our factory, holds the record for the highest altitude paraglider deployment at 65,000 feet, a little above 65,000 feet, and was able to fly a ground track path of over 160 miles autonomously.
When you're designing for speed over longevity, what are some systems engineering or design trade-offs?
I've organized our engineering department strongly around the responsible engineer model. I've always felt that that is the best way to get the best product and also the best satisfaction out of people and the fastest speeds. So it's really centered around having engineers have true ownership over a part of the system. And that means that they're responsible. If it has a problem, it's not dump it on the system engineer. It's a problem with their system and they have to solve it, and they have to coordinate as required between other systems to ensure that the broader vehicle still functions as required. And that has certainly been something that we've been hiring for in particular. It's something that SpaceX and a lot of the leaders in the space startup realm are also using, and it's because it works.
The Carry-All Block 1 mission is in 2020. Some years later, you're mass manufacturing the spacecraft. What supply chain bottlenecks of today stymie that roadmap?
Good one. So our first launch is in 2027, just so that it's not an error on there. We haven't claimed 2026. One of the biggest supply chain pieces to it actually is the paraglider. So paragliders right now are pretty much only exclusively manufactured in Southeast Asia, and especially when you're talking to a military customer, it's very important that certain things be built in the US. So for us, and there's some legal federal acquisition regulations, especially related to these types of things. For us, we actually, right behind me, is the first paraglider manufacturing facility in the US. We are doing US-based manufacturing and bringing that in-house, both for the supply chain piece of it, and also the quality pieces of it, bringing it up to a true aerospace standard, and additionally allowing us to have control over the design, because the sport paraglider world, which we've done a lot of our early proof of concepts using, isn't really designed to deploy people at 65,000 feet. It actually isn't even really designed to deploy. They're usually, people will open them up on a hillside and then run down the hillside and start flying. So bringing that design in-house really gives us that control over fine-tuning it for our exact use case, and also really bringing in that U.S. manufacturing base. We recently had a SOCOM general in here, a very, very senior member of the military, and he loved our product. He loved hearing about AirDrop, but I'll say the thing he really walked away with that he wanted to go and tell a lot of people about was how happy he was to see that manufacturing coming in. It'll really be a true... One of these days, once we're reaching that scale, it will definitely be a case where we've got a bunch of sewing machines and a bunch of technicians just humming along, and it will really feel like a true U.S. manufacturing base and industrial piece.
Out of curiosity, how large is your facility?
So we are currently located in sunny Playa Vista, which is right by the LAX airport for anyone who wants to come visit us. And we are in, I believe, 16,000 square feet. Of that, about 12,000 is factory space, and we have called dibs on the building next door, which is from the same real estate group. And I'll say too, we have it's a unique vision of a space company manufacturing line. We sort of see it as our ultimate end goal is closer to, say, an automotive repair shop than it is to a traditional, like, ultra clean, ultra sterile environment. And we see that because once we are launching and we're having vehicles re-enter and they're reusable, it's almost like we'll have fresh vehicles go out one door, and then they'll go to space and they'll come back, and they'll come back in the other door, charred a little bit, and then we refurbish them, and then we send them back out that door, and we end up with this continuous loop of vehicles coming in that have, this one's on its third flight, and this one's on its 12th flight or something, and then it's just bringing them back up to speed. You see now, especially with like SpaceX boosters, they've got a little healthy char on the outside, and I think we'll end up seeing some of the same of, you got that little bit of toastiness to some of the vehicles.
And when faced with a challenging integration, how do you decide whether to pivot or to push?
Well, I think challenging integration is usually a result of previous sins when it comes to aerospace. Everyone knows that integration and test always gets the short end of the stick because schedule gets consumed early on when everything seems so far out in the future. And then by the end of many space missions, which is something that I certainly saw in prior roles with satellites, is by the end you're looking at your clock in shifts, in like hours of activity. And back in, the 8 months prior to that, you were just throwing out, oh, we don't have to have this meeting today, we'll have it tomorrow. But at Outpost, we care deeply about maintaining that sense of urgency and realizing that a day is a day is a day, and that a slip of, a review that's a year before launch, a slip of that by a day is exactly the same slip as when you're one day from the launch pad. And just keeping that ever present in our minds and realizing that we know that things will go wrong. You will have challenges in integration, even if with the best planning, and making sure that as you're going through the process that you're maintaining schedule margins so that you can survive it when it comes.
Eventually, you're planning high cadence reentries. Is there a future for a cargo fast pass in space?
A cargo fast pass. Ooh, that's a fun one. Well, actually, kind of, yes. That's kind of what the point-to-point logistics model, especially for the military customers or the farther future of a FedEx competitor, so to speak, where you could have, and we've envisioned and talked about with customers as part of the rocket cargo program, which is currently out of AFRL, Air Force Research Labs. The rocket cargo program envisions having basically warehouses of pre-packaged boxes of material, and then you have vehicles. And so think of it kind of like the Amazon picking warehouse, where they've got boxes, they've got stuff, and they've already got like a pre-packaged box that just could be pulled off a shelf, shoved into a carry-all, that carry-all shoved onto the rocket, and then launched and landed. And so that's kind of you're in the fast pass because you're like on deck for a launch. So yeah, you could have priority shipments. You could have, I don't know, for whatever kind of material you could stipulate, but having that priority access to a system like this that truly gets something across the planet, faster than a plane could get there, faster than a plane could, get out of the airport and out of the flight pattern, so to speak.
What's the biggest technical constraint preventing you from flying, say, 100,000 tons over the 10 tons right now?
10 tons is already a lot, so usually no one asks me about, can you make it bigger? I think you find optimizations when it comes to logistics that certain sizes become valuable. When you put too many things all together at once, then the problem is that there's very few things that you want that are that big. And so you end up just putting a collection of smaller things on the system. So it seems like in Earth logistics that something on the order of a 10-foot shipping container is a very valuable size. And so optimizing for that makes good sense when it comes to things like space stations as well. If we think about, commercial LEO destinations and the growth of commercial stations with humans on them, even, that we expect to see in the next decade. It's almost like getting supplies to like an island outpost or something. They still want a shipping container. And a piece of it is why we call ourselves Outpost too, that it's really getting those supplies to that farther spot.
Years later, when Outpost wins, how does the world look different for your customers?
Because we have a true dual use technology, so it really does satisfy both government customers and commercial customers. There's some different pieces to it. On more of the government side, we look at it as, one of these days we're going to have a roster of names. Well, we'll never be able to see it, but we know that it'll exist. Like a roster of names of people who made it back to their families, of like warfighters who made it back to their families because of our system. And like even just saying that kind of brings chills, right? Like knowing that this will be the thing that decides that someone gets back to their kids, which as a parent myself, it's just that benefit alone would make this worth it. Then on the other side of the house, the commercial customers, it's the same thing. There's going to be a roster of people where their life was saved because of whatever pharmaceutical got made in space. Or on the other side, talking more to the AI computing universe, the fiber optics that we're making will be completely game-changing for the AI companies, for telecom. We could end up with, we will end up with a future where in-space fiber wins out over ground-based fiber, and it becomes the de facto standard. And so it's almost like we will end up with this nervous system of Outpost-developed fiber optics that connect the globe. So it really is about that connection across the world, and that connecting things through time, connecting things through data once it's back on the ground, or the bringing together these different elements.
Is there a future where you're optimizing beyond LEO into geo, cislunar, planetary, just-in-time logistics? And if so, how does your approach change?
We are a system that, as far as terrestrial landings, we require an atmosphere. We depend on aerobraking. That being said, we've actually had study contracts with NASA to investigate landing our system on non-Earth terrestrial. So particularly looking at Mars reentries and also at Venus reentries, those being more for science missions or maybe for our future Mars base. But yes, it's definitely an application. We can move beyond LEO if there's a value proposition that makes sense. Certainly in the cislunar environment, we know that, something like a gateway or something put in any station in a lunar orbit would also need cargo resupply, and they will presumably have valuable cargo come back. There's a very realistic chance that we're developing the system that, for example, gets back some of the moon rocks from a lot of the moon activity that's coming up here as well. I spent a time of my career at NASA JPL, which had been developing the Mars sample return concept. And I'll say, you're never going to send the system from the ground all the way back to Earth. It's more of, you have one system, get it into orbit, and then you have another system, take it from orbit and back. And so a carry-all would work very well for that from lunar orbit back version. And same thing for anyone, we talk about moon mining, and everyone thinks space or moon rocks, but for any of those helium-3 fans out there, a carry-all would carry an absolutely ungodly valuable amount of helium-3. So just come talk to us.
You mentioned the mission in 2027. What makes it a success? What's your North Star metric?
So this first mission will be really a demonstration that the concept, truly works. The proof is always in the pudding, right? And for this one in particular, it will be the validation of the heat shield dynamics. All the simulations, all the math says it works. All of the experts out of NASA say it will work. But of course, you have to get it to work. So our primary goals for this mission is proving that we can get through the hypersonic to subsonic regime, and then deploy the paraglider. And, if we land and stab it on the target, that would be my favorite. But I'd say that the primary goal, number one, is proving the heat shield works, and then that will follow on for our second mission. The second mission is late 27 or early 28.
So what should we look forward to seeing from you from Outpost Space over the next 3 months?
These next few months, we'll be doing a number of demos to our military customers that will be very exciting, that will certainly be getting video out for people to see. And a big piece of that is the AirDrop product, which is using our system, but just the in the atmosphere portion to use for military logistics and their mission sets.
And Julie, how does your storytelling change when speaking with defense customers versus commercial customers?
I would say some of the military customer, and it's different even within, it's not like it's one giant monolith of the military. There's different players within the group. Some actually prefer the smaller vehicle over the larger vehicle, that they're more interested in, say, the smaller version because that's all the payload they care about, or they care more about the fact that our system is actually very low observable. So it has a very low radar cross-section just by the nature of the system, and it has very unique thermal characteristics that would make it undetectable to a lot of existing systems. So they actually like the small version. Then we have other military customers where they just want to move the biggest box they can around the globe as fast as possible. And then, like I said, we have some military customers that want to pre-position in orbit. We have others that want to just do the point-to-point logistics. And most of those customers similarly like the AirDrop products for the exact same reasons, and like the small AirDrop versus the big AirDrop, for example, or the big AirDrop over the small. Then on the commercial side, they're really looking more at the unit economics of doing a full mission, right? At the end of the day, the military cares about the value and the speed especially, and on the commercial side, they're usually willing to be a little bit slower if they can have a higher value, for example. And we're getting calls every day now from different space companies who are looking at flying demos on even some of our first early missions. We will take any opportunity, even if we don't need you to guarantee that it survives on the first launch. Like, we want to be on your first launch. We're like, okay, there's only so much space on it, but we appreciate it. And on that side too, some customers care more about the environment for it. We keep joking that one of these days we're going to fly like a Fabergé egg just to prove to everyone, like, no, really, the system is actually, it's not any harder than going to space, is coming back from space with our system.
How can space operators, tranches of the government, contact you or Outpost Space?
So find our website, outpost.space, and scroll down all the way down to the bottom. There's all the contact information there. Find us all on LinkedIn. I'll also do the pitch of, we're growing, we're constantly hiring. I need great engineers who want to solve cool problems just like me and just like the rest of the team. And if having high ownership over the product and having that real go-getter attitude with the associated humility and not arrogance, that's what we're looking for.
Thank you, Julie. This has been Space Terminal. I'm Zuni from Imagining Forward. New episodes are out every week. You can find Julie Newman and Outpost Space in the show notes. You can also look up Outpost Space on our intelligence tool at imaginingforward.space. Thank you.